All right, in this video, we are going to read section 3.8, which is on implicit differentiation. Okay, so the learning objectives here are 3.8.1. Find the derivative of a complicated function by using implicit differentiation. 3.82, use implicit differentiation to determine the equation of a tangent line. Okay, so we have already studied how to find equations of tangent lines to functions and the rate of change of a function at a specific point. In all these cases, we had the explicit equation for the function and differentiated these functions explicitly. Suppose instead we want to determine the equation of a tangent line to an arbitrary curve or the rate of change of an arbitrary curve at a point. In this section, we solve these problems by finding the derivative of functions that define y implicitly in terms of x. Okay, so there's a lot there in that paragraph, but we're going to break it all down here in the rest of the section. So what is implicit differentiation? It says, in most discussions of math, the dependent variable y is a function of x. When that is true, we express y in terms of x. If this is the case, we say that y is an explicit function of x. And so we'll give, y as an explicit function of x. For example, when we write the equation y equals x squared plus 1, we are defining y explicitly in terms of x. So with y being equal to x squared plus 1, a lot of times we'll write that as f of x equals x squared plus 1. Right? Y is being written as a function in terms of x. So y can be written as a function of x and only x. On the other hand, if the relationship between the function y and the variable x is expressed by an equation where y is not expressed entirely in terms of x, we say that the equation defines y implicitly in terms of x. For example, the equation y minus x squared equals 1 defines the function y equals x squared plus 1 implicitly. So implicit, and there's explicit. So, or maybe we can put explicitly and implicitly. Explicitly defined in terms of x, that would be where y is equal to x squared plus 1. That's the equation we gave up above. But if we subtract the x squared to the other side, we could write this as y minus x squared equals 1. Here we say that y is implicitly defined in terms of x, but not explicitly defined in terms of x, because here's an equation. Basically, y is not solved for. Y is not isolated in the implicit equation. When it's explicit, y is solved for, and it is written entirely in terms of x. Implicit differentiation allows us to find slopes of tangents to curves that are not clearly functions, or that are clearly not functions. They fail the vertical line test. We are using the idea that portions of y are functions that satisfy the given equation, but that y is not actually a function of x. In general, an equation defines a function implicitly if the function satisfies that equation. An equation may define many different functions implicitly. For example, the functions y equals the square root of 25 minus x squared and y equals the square root of 25 minus x squared if x is between -5 and 0, and negative 25, the square root of 25 minus x squared if x is between 0 and, that should be 5 actually, which are illustrated in figure 3.30, are just 3 of the many functions defined implicitly by the equation x squared plus y squared equals 25. So here, all it's saying is, okay, so there is an equation here, x squared plus y squared equals 25. And this is not a function, right? If you might recognize this from previous class, it turns out that this is the equation of a circle of radius 5. X squared plus y squared equals 5 squared gives us a circle of radius 5. And we can draw this circle here. And you can see that this is not a function because it fails the vertical line test. Okay, well, so this is not a function. Then that means it can't be written as, we can't write this as f of x equals, we can't write the equation of this circle as f of x equals something, because, well, this is not a function, first of all, so we can't use function notation on it. We can't define it explicitly in terms of x. We need an equation like this. Okay, but if you write the equation like y equals the square root of 25 minus x squared, and here for the values of x, where x is between -5 and let's say x is between -5 and 0. That's one of the portions that they give up above. This equation, if we plug this y into the equation here, well, let's do it. It's x squared plus y squared, and y is equal to the square root of 25 minus x squared. And since y is being squared in the implicit equation, we square this quantity, and this is equal to 5 squared, which is 25. And notice that we get x squared plus the square and the square root cancel, so we get 25 minus x squared equals 25. And then the x squareds cancel, so we get 25 equals 25. This is a true statement. So it says that this equation here, when plugged into the other equation, since it produces a true statement, that means that their graphs coincide. So let's graph this purple portion on the same as the green graph. For x being equal to -5 up to 0, that would be this portion here, right? So notice that the green equation, x squared plus y squared equals 5 squared, implicitly has y in it, and it defines a circle. Its graph is a circle. And the purple equation, even though it is in the purple equation is y explicitly in terms of x, it only gives a portion of the circle. Okay, so let's take a look here, and this is kind of what it was talking about there. It gives, that you can give various equations. So notice only the one that has y implicitly in it, this one cannot be solved for y and have a function, have the form of a function, because, well, this circle here is not a function. So the various equations you could give are this equation here. When you put no restriction on x, well, x can range from -5 to 5. It gives us the upper half circle. If you put a negative sign in front of it, that gives us the lower half circle. And then, for this one here, they actually fixed the mistake. From -5 to 0, that's the portion that we talked about just a moment ago. That's this one here. And then if you put the negative sign in front of the square root and then allow x to range from 0 to 5, that gives you the lower half of the circle on the right-hand side. Okay, so there's a bunch of different ways to write equations that satisfy the implicitly defined equation. Let's continue reading. So here we go. Well, it says the equation x squared plus y squared equals 25 defines many functions implicitly. If we want to find the slope of the tangent line to the graph x squared plus y squared equals 25 at the point 3, 4, so let's see, where would that be? 3, 4 would be somewhere right here. What's the equation of this tangent line here? Okay. we could evaluate the derivative of the function y equals the square root of 25 minus x squared at x equals 3. On the other hand, if we want the slope of the tangent line at the point 3, -4, so 3, -4 would be the point, just down below 3, +4. Right? So can we find the slope of the tangent line for both of these lines from one equation? Well, if you look at the equation of a function, well, you either have the top point or you have the bottom point. But you can't really have both, because if you have both of these from one equation of a function, well, that can't happen because this is not a function, right? They both have the same x coordinate. So it says, on the other hand, if we want the slope of the tangent line at 3, -4, we could use the derivative of a different equation, the one with the negative in front of it. That's the lower half circle. However, it is not always easy to solve for a function defined implicitly by an equation. Fortunately, the technique of implicit differentiation allows us to find the derivative of an implicitly defined function without ever solving for the function explicitly. The process of finding dy dx using implicit differentiation is described in the following problem-solving strategy. So the problem-solving strategy for implicit differentiation says to perform implicit differentiation on an equation that defines a function y implicitly in terms of a variable x, use the following steps. Take the derivative of both sides of the equation. And we'll put a stress on the word both here, because a lot of people always forget to do both sides. They'll do usually one side. Keep in mind that y is a function of x. Consequently, whereas d dx of sine x is equal to cosine x, we need to keep in mind that d dy of sine y is going to be the cosine of y, but then using the chain rule, since y is the argument of sine and y is a function of x, we have, a function inside of a function. So we need to use the chain rule and multiply by the inner function. The inner function is y, the derivative of y, we will write with the notation dy dx, because we must use the chain rule to differentiate sine y with respect to x. Rewrite the equation so that all terms containing dy dx are on the left, and all terms that do not contain dy dx are on the right. Factor out dy dx on the left. Solve for dy dx by dividing both sides of the equation by an appropriate algebraic expression. Okay, so let's go ahead and take a look at the derivative of an equation where y is implicitly defined. Okay, so, and I'll do this on the side here, just to kind of write out the steps. X squared plus y squared equals 25. This is the equation of a circle. And so what we do is we start by applying the derivative to both sides, the left and the right. Okay, well, let's go ahead and see d dx of, we're going to apply it to all the terms. The derivative of 25 is 0, so I'll go ahead and put 0 there. Now the first term was x squared, the second term was y squared. So what is the derivative with respect to x of x squared? We all know that that is 2x. Plus, what is the derivative with respect to x of y squared? Here we have a composition of two functions. The outer function is the squaring function, so we will use the chain rule, and we bring down the exponent, we leave the base the same, and we subtract one from the exponent. Then we have to multiply by the derivative of the inner function. The inner function here is y. The derivative of y with respect to x, we will call dy dx. And notice, now we have one term with dy dx in it. That is the derivative of y that we're looking for. The other, that's a 1 there. And so now we can just solve for dy dx. Let's go ahead and subtract 2x. And so we get 2y dy dx is equal to negative 2x. And then we divide both sides by 2y. And so we get, on the left-hand side, dy dx is equal to negative, the 2's cancel, so we'll write this negative x over y. And that is our derivative. This is the derivative of y with respect to x. You could even call it y prime if you'd like. Y prime is equal to negative x over y. And notice that it is the derivative, but it's not even purely in terms of x. It also has a y in it, which is okay. So if we wanted to find, let's say, remember they asked before, they had 2 points. We wanted to find the slope of the tangent line at 3, 4, or the slope of the tangent line at 3, negative 4. Well, now we can find both of those. Let's go ahead and take a look at how we would do that. Let's say the derivative y prime, and I'll put parentheses here, at the point 3, 4. This is going to be the opposite of 3 over 4, right? My x just becomes 3, my y becomes 4. We get a negative slope there. What about for the other point, y prime evaluated at 3, negative 4? Well, that would be negative, from the negative x. The x is 3, the y is negative 4. There's 2 negatives there, so we get a positive slope of 3/4. So notice negative slope of 3/4, positive slope of 3/4. Let's see if this corresponds to the graphs. Yes, it does. Negative slope, the slope is 3/4. And then positive slope, positive 3/4. And notice that we found both of these slopes from a single derivative. We didn't have to use 2 different functions like here and here to find the slope of each of those individual tangent lines. We were able to do it using implicit differentiation basically in with one equation. Okay, so what did we do? We applied the derivative to both sides. So basically that amounts to taking the derivative of every term. Now, here is an important part. When we take the derivative of, we're taking the derivative with respect to x. This is a function, this is y, which is a function of x, and it is being squared. So we need the chain rule here. So we need to take the derivative of any y term, as you normally would, and then remember the chain rule that asks us to multiply by the derivative of the inner function. The derivative of the inner function, y, is dy dx. And then we just solve for dy dx. Note that the resulting expression for dy dx is in terms of both the independent variable x and the dependent variable y. Although in some cases it may be possible to express dy dx in terms of x only, it is generally not possible to do so. Okay, so let's do another problem here. Using implicit differentiation and the product rule. Okay, so let's go ahead and take a look at this one. So how would we do this? Let's see. We have x cubed times the sine of y plus y equals 4x plus 3. And so we are going to apply the derivative basically to every term. When we apply it to both sides, we're pretty much applying it to every term. So I'm just going to apply it to each term to begin with. Okay, and then let's go ahead and, let's start with this first product here. The derivative of the product of x cubed times sine of y. And we know the product rule from a previous section. Let's go ahead and now use that product rule. So the product rule is, as I like to call it, fig-gif. I'm going to write it out here with more steps, just to make sure that we understand where every piece comes from, since we are using implicit differentiation. But fig is the derivative of f, that is the first function, times g, the second function, sine y, plus gif, g prime f, that is the derivative of the sine of y, g prime f. F is x cubed. Plus, now the derivative of y with respect to x, we can just leave that as dy dx. That is the derivative of y with respect to x. On the other side of the equal sign, the derivative of 4x with respect to x, that's just 4, and the derivative of the constant 3 is 0. Okay, so let's go ahead and take the derivatives now. On that first part, the derivative of x cubed is 3x squared. Sine y, nothing's happening to that. That's just sine y. Now here we have the derivative with respect to x of a composition of functions. The composition here of functions is the sine of x is the outside function. The inside function is just y. And so we need to take the derivative of the outside function, which is the cosine. The inside function stays the same, y. Then we multiply by the derivative of the inner function. The derivative of the inner function y is dy dx. And then there was a factor of x cubed there. Plus dy dx equals 4. Now, the third step of our problem-solving strategy did ask us to get rid of or subtract any terms, move all the terms that don't have a dy dx to the other side, and the terms that do have dy dx, leave them on the same side. So, okay, let's go ahead and do that. The reason that we do that is because if we have dy dx terms all on one side and nothing else, we can factor out dy dx. Let's go ahead and factor that out from both of these terms. And we would be left with, I'm going to do a little bit of rearranging here, just x cubed times the cosine of y plus, and then dy dx, we factor out dy dx, that leaves us just with a factor of 1. Now you can do your own distribution here to double check that that's the same as the previous expression, and it is. And on the other side, we have the 4 minus 3x squared sine y. Now all we have to do is divide by this factor here. If we divide by that factor, we have dy dx all by itself, and that would be our answer. So dy dx is equal to 4 minus 3x squared sine y divided by x cubed cosine y plus 1. This is our answer. That is the derivative of y with respect to x. Notice again, it's in terms of both y and x, not just x, and that's perfectly fine. Okay, so let's read, or just quickly look at the steps. We apply the derivative to both sides. Very good. That basically means applying the derivative to each term. Okay, now the first term was a product, so we had to apply the product rule, which they did, f prime times g plus g prime times f. And then the derivative of, the next term was the derivative of y with respect to x. We're just going to leave that as dy dx. And then, of course, we want to pay close attention to here, what is the derivative of sine y with respect to x? Well, since it's a composition of functions, that would be the derivative of the outside, which is cosine of y, times the derivative of the inside function, dy dx. And then, as we did, move over the 3x squared to the other side. We have two terms that have dy dx in them, so we factor that out and divide. And we have our derivative. Okay, so what if we want to find a second derivative? Well, that's actually not too hard. We just find the derivative twice, right? So here we are asked to find the second derivative, basically, of y for the equation x squared plus y squared equals 25. Well, yeah, in a previous in the previous example, the first example, we found that dy dx for this equation here was negative x over y. So we are going to apply the derivative function again. We're going to derive this with respect to x. and see what that gives us. On the left-hand side, the notation would be d squared dx squared, and then we're applying this to y. So this is the second derivative of y. Now, what are we going to have to use on the right-hand side? This is a quotient on the right-hand side, so we're going to use the quotient rule. Remember, the quotient rule is fig minus gif over g squared. Okay, so the top function, the numerator, we'll say is negative x. The denominator, call it g for right now, is y. And so if we want to find f prime, that's not difficult to do. F prime is equal to -1, and then g prime is equal to, what's the derivative of y? The derivative of y with respect to x is dy dx. So let's go ahead and assemble our quotient rule derivative. F prime is -1 times g, g is y, minus g prime is dy dx, times f is -x, divided by g squared. G is y, and that is squared. And so we can simplify here. We get -y plus x dy dx over y squared. Now, can this be simplified? The answer is yes, because there is a dy dx here, but we know that dy dx from the previous problem, right? We stated it just a moment ago, dy dx is -x over y. So we can make that substitution if we want to. Let's go ahead and do that. This is -y plus x times -x over y over y squared. And what does this give us here? This gives us -y minus x squared over y divided by y squared. And can we simplify this further? Yeah, it just depends on how far we want to simplify. What else could we do here? I could multiply this by y on the bottom and y on the top, right? So add another, basically multiply a factor of y to the bottom of the -y and to the top. So it becomes a minus y squared over y, which is, if we reduce that, that's minus y. And the reason I did that is now I can combine the two factors, the two fractions in the numerator, and we would get minus y squared minus x squared over y divided by y squared. And if you remember from arithmetic here, how do you divide fractions? You basically multiply by the reciprocal of the bottom fraction. The reciprocal of the bottom fraction is 1 over y squared. And if we multiply these two together, we would get minus y squared minus x squared over y cubed. Okay, and I will leave it like that. I haven't looked at the solution myself, so I don't know how far they simplified this. You could try to simplify further. It won't simplify much past that. So let's go ahead and take a look. So yeah, they use the quotient rule. That is correct. Then they simplify. Notice that dy dx got replaced by -x over y. And yeah, they ended up with the exact same answer. They simplified and left it like this, how we did as well. Okay, at this point, we have found an expression for the second derivative. It says if we choose, yeah, we can simplify the expression further by recalling that x squared plus y squared equals 25. That's a good point, actually. And making the substitution in the numerator, and we obtain the second derivative of y with respect to x is 25 over y cubed with a negative in front of it. Yeah, that's a good point. So we'll write that out. I mean, like I said, it doesn't really matter. But if you factor out a negative from the top, you get y squared plus x squared over y cubed. And if you remember, the original equation was x squared plus y squared equals 25. So we can plug in a 25 there. And that's good. All right, that's just simplification. That's fine. Okay, so how do we find tangent lines implicitly? Well, this should be fairly simple because tangent lines, we've been doing this for a little while already. You find the derivative, you plug in the coordinates of your point, where you want the tangent line to be tangent to. There's a point, has two coordinates, and then you plug in those coordinates into the derivative. That gives you the slope of the tangent line, and then you use the point slope form to find the equation of the tangent line. So let's go ahead and take a look. Basically, it's going to be the toughest part of it is going to be still finding the derivatives. And then now you just have to find the equation of line using those derivatives, which we learned in a previous class called algebra. Okay, so now that we have seen the technique of implicit differentiation, we can apply it to the problem of finding equations of tangent lines to curves described by equations. Okay, so, and this is actually the problem we did earlier, right? Finding a tangent line to a circle. Find the equation of the tangent of the line tangent to the curve x squared plus y squared equals 25 at the point 3, -4. And so, okay, well, here's the point that they gave us. It has an x coordinate. We can call it x1 if you want, and y1. This is the point that they gave us. And if you remember from earlier, this circle looks something like this. The point 3, -4 is somewhere here. And, we saw that it had a positive slope. Now, in a previous example problem, the first example problem we did, we found that dy dx for this curve here was -x over y. And then we mentioned that if we evaluate this dy dx, and it is evaluated at 3, -4, we plug in those values, we get minus x, 3, over y, which is -4. And so that gives us a positive 3/4, which is our slope of our tangent line. And this is what we actually showed this earlier. Okay, so we have that slope, and then we have our point. And so now we can easily just plug into y minus y1 equals m times x minus x1. This is the point slope form. For the equation of a line. And so we just plug in what we know, y minus y1 equals m times x minus x1. x1 is 3. And so now we, y, the double negatives there cancel, become positive 4 equals 3/4 x minus, and here we can say that that is minus 9/4. And then finally, we can just solve this for y. We can subtract 4 on both sides. If I subtract 4, well, we need a common denominator here to be able to actually subtract these fractions. So we can multiply by 4 on the bottom, 4 on the top. And so we get -9/4 minus 16/4. And this is -25/4. So the equation of our line is y equals 3/4 x minus 25/4. And that is the equation. Now, is this believable? Definitely the positive slope is believable because you can see there's a positive slope on the line. So 3/4 seems right. And then the y-intercept of this, the y-intercept here, remember, is where this line would intersect the y-axis. And if you look at that, line, it's just a rough sketch, but you can see it's a negative value at least. Well, we take a look at the solution, and yes, this is the correct answer. All right, very nice. Cool. Ooh, this is a nice curve here. Definitely not a function, right? Because it does not pass the vertical line test. So there is no function notation equation for this graph here. But this graph can be defined implicitly. And so the equation we're given is in terms of x and in terms of y. So let's find the equation of the tangent line to the graph of y cubed plus x cubed minus 3xy equals 0 at the point 3 halves, 3 halves. This curve is known as the folium or leaf of Descartes. Ooh, very nice. So let's pretend like we don't have the equation of this, or the graph here. Let's just suppose we are just given this problem here. And so we have this equation, y cubed plus x cubed minus 3xy equals 0. And so we want to take the derivative of both sides. And so the derivative of y cubed, what is that? That is 3y squared. But remember, we're taking the derivative of y with respect to x. So we need to multiply by the derivative of the inner function here. The inner function is y. The derivative of y is dy dx. Plus, here, x cubed, this is 3x squared. If you wanted to do the same thing and say, okay, well, we'll multiply by the derivative of x with respect to x, well, that's just 1, the derivative of the inner function. You could use a chain rule here if you wanted to, but that would just be a factor of 1 and, not really give us anything useful. Minus, and here we have minus the derivative of a product 3xy. We're going to have to use the product rule, and remember that we're taking the derivative of a y in there, so we're going to end up getting a dy dx somewhere. So we'll take the first factor here to be, or the first function to be 3x, and then the second function to be y. And so what is the derivative here? I'm gonna write out the chain rule, d dx of 3x. That's f prime times g plus g prime. That's the derivative of y with respect to x times f, which is 3x. And this is equal to the derivative of 0, which is 0. Now, of course, we do need these brackets here because there was a negative on the outside, and that negative is applied to this entire product here. The negative was applied to the entire product, so the negative should be applied to the entire derivative of the product. So we do need those parentheses there. Okay, or those brackets. Okay, so then let's go ahead and simplify here. We have 3y squared dy dx plus 3x squared minus the derivative of 3x with respect to x is 3. So we have minus 3y. I'll apply the negative at the same time. And then I'm going to apply the negative here. And then we have minus 3x, and then the derivative of y, that usually gets put last, so we'll put it at the end, dy dx equals 0. Now, part of the procedure here, the next step, once we've differentiated, was to move all the terms that don't have a dy dx to the other side. This 3x squared does not, so we will subtract 3x squared on both sides. And now notice we only have terms that have dy dx in them on the left-hand side. And so we factor out that dy dx. What's going to be left as the other factor? Well, it's just going to be 3y squared minus 3x equals 3y minus 3x squared. And then we can divide both sides by 3y squared minus 3x, divide by 3y squared minus 3x, and we get dy dx is equal to 3y minus 3x squared over 3y squared minus 3x, and that is our answer. Or at least that's the derivative, right? we want the whole equation of the line. So let's go ahead and find the slope of this tangent line. That would be by evaluating the derivative dy dx at the point 3/2, comma 3/2. Now, is this going to be easy to do? Yeah, kind of. One thing that we should notice here actually is that the 3's cancel, right? There's a 3 on both factors. So we could factor out a 3 from the top. We could factor out a 3 from the bottom, and then the 3's would all cancel. So let's go ahead and do that. And so let's simplify here. And this is just y minus x squared over y squared minus x. And so we'll consider this the derivative. I mean, that is the derivative. It's just more simplified. So what are we going to get here? Well, let's go ahead and plug in. Y is 3/2 minus x is 3/2 squared over y squared minus x, y squared minus x. And notice if you take a close look at this, the top and the bottom, they're just opposites of each other. I guess we could do the arithmetic here. If you square 3/2, right? I'm going to work, or let's do the bottom first here. Squaring 3/2 on the bottom, this is going to give us 9/4. So we might as well multiply the other factor by 2/2. That way we can make this minus 3/2 into minus 6/4. So they have the same denominator. And then, so of course, we can do that, on the numerator. And in the numerator, we get 6/4 minus 9/4. And so on the top, we get -3/4. On the bottom, we get +3/4. Whenever you divide a number by its opposite, the answer is -1. So the slope of this line is equal to -1. So m, the slope is -1. The point x1 comma y1 is 3/2, 3/2. And so we use our point slope form, y minus y1 equals m times x minus x1. And just plug in y minus 3/2 equals m, -1, times x minus 3/2. So what do we get here? Let's go ahead and add 3/2 to both sides. And we have our answer of y equals -x plus 3/2 plus 3/2. And we can write this as -x plus 6/2. And 6/2 we know is just 3. So this is -x plus 3. Or y equals -x plus 3. Okay, and that's our answer. Now, of course, if you look at the graph and you're really good at reading graphs, you could have seen this right away, because that's why I said, assume that we were only given this problem here rather than the graph. In general, you will not have the graph ahead of time. But if you look at the equation of this line here, well, you can see that the y-intercept, b, is equal to 3 for the y equals mx plus b. So we would know that that's 3. And then the slope here, the rise over, so if you look at the rise here, over the run from, let's say, this y-intercept to the x-intercept, the rise is -3, the run is +3. So rise over run is -3 over +3, which gives us y equals -x plus 3. And you can get the equation very easily just by inspecting the graph. But in general, you don't have the function already graphed, and there's no calculus in this. That's just, that's kind of cheating there. But okay, so there we have our solution, exactly what we did. So let's go ahead and move on. All right, and how many more examples do we have? I believe we have one more, yes. Okay. So let's end here with example 3.73, applying implicit differentiation. Okay, so this is an application problem. Let's see. In a simple video game, a rocket travels in an elliptical orbit whose path is described by the equation 4x squared plus 25y squared equals 100. So that's the equation of an ellipse. Okay, very good. And let's review a little bit, I guess, on ellipses. For the ellipse here, if we wanted to graph it, usually we would divide by 100. So I won't go into too much detail here for graphing ellipses. We can reduce each of these fractions. The reason we divided by 100 is because the equation for an ellipse, a lot of times we want it to be equal to 1. And so that gives us a lot of information about the ellipse. And so this equation is just x squared over 5 squared plus y squared over 2 squared, which is equal to 1. And so what this tells us is this ellipse is going to be centered at 0, 0. And in the x direction, it is going to be 5 units wide from the origin to both the left and right. So if we go 1, 2, 3, 4, 5, 1, 2, 3, 4, 5, we have these 2 points here. In the y direction, it's going to be 2 units tall and both up and down. And so this is what our ellipse roughly looks like here. Here's a pretty good sketch of our ellipse. And now the reason that I wanted to do that was just so we could kind of guesstimate what the equation of the line would be if we're going to find a tangent line. So it says the rocket so there is a rocket traveling in this elliptical orbit. The rocket can fire missiles along lines tangent to its path. The object of the game is to destroy an incoming asteroid traveling along the positive x-axis towards 0, 0. If the rocket fires a missile when it is located at the point 3, 8/5, where will it intersect the x-axis? Okay, so we are told that, let's take a look here. And let me move this graph over just a little bit here so we can draw on it. There is an asteroid traveling along the positive x-axis, so somewhere over here toward, the point 0, 0, which is the origin, right? If the rocket fires a missile when it is located at the point 3, 8/5, so 1, 2, 3, 8/5, the rocket I will draw in blue. So that is this point here. Where will this rocket intersect, or this missile intersect the x-axis? And it's going to be a point right here. It looks like it's past the x value of 5. And so let's go ahead and find that value of x. So, well, what do we need to do? Basically, we need to find the equation of the tangent line and then find the x-intercept for that equation of the tangent line. Okay, so let's go ahead and get started. 4x squared plus 25y squared equals 100. We take the derivative of each term of both the left side of the equation and the right side of the equation. The derivative of 4x squared with respect to x, that's just 8x, nice and simple. Now the derivative of 25y squared with respect to x, we're going to take the derivative as usual. The 25, we multiply by the exponent of 2, that's 50, y to the first power. Then we have to multiply by the derivative of the inner function here, the inner function is y, the derivative of y with respect to x is dy dx. And then the derivative of 100 is 0. Then we can solve this equation for dy dx. So we have dy dx equals, so we have a minus 8x on that side, and then of course we would end up having to divide by this 50y. So let's go ahead and do that at the same time, divided by 50y. And this is essentially our answer. We can reduce by a factor of 2 and get negative 4x over 25y. So this is our derivative. The derivative will give us the slope of the tangent line. So let's go ahead and find the slope of the tangent line. The x value and the y value were given. So dy dx, the slope at the point 3,8 is equal to negative 4 times x, which is 3, over 25 times y. Y here is 8 over 5. And so we simplify. This is negative 12 over 40. 8 times 25 is 200, divided by 5 is 40. We can reduce this by 4. And we get negative 3 over 10. This is our slope of our tangent line. Once we have the slope of the tangent line, we can then use that along with the point, plug into the point slope form. The point slope form, remember, was y minus y1 equals m times x minus x1. y1 was, the y value given was 8/5. M we just found to be negative 3/10. And then x was 3. So this officially is our answer here, but we can simplify this equation to put it in slope intercept form. And that is going to be, swipe it over this way, y minus 8/5 equals negative 3/10 x if we distribute, plus 9/10. And then if we want tenths, we got to multiply by 2 on both the top and bottom. So that's going to be negative 16 over 10, which we will add to both sides to cancel out the negative 16 over 10. We add positive 16 over 10. And so we have our equation as y equals negative 3/10 x plus 25 over 10. This is the equation of our line, and we wanted to find the x-intercept of this line. The x-intercept occurs when y equals 0, so we will just plug in 0 into our equation for the line. 0 equals negative 3/10 x plus 25 over 10. We can multiply both sides of this equation by 10. The reason that we do that is because, well, 10 times 0, that's just 0. But when we multiply 10 to both of these, when we distribute a 10 here, the denominator is going to cancel, leaving us with no fractions. So 0 equals negative 3x plus 25. We can subtract 25 from both sides. If we do that, we get negative 25 equals negative 3x. And then divide by a negative 3 on both sides. And so we get 25 over 3, the negatives would cancel, equals x. This is approximately equal to 8.33 repeating. So that is the location where it would intersect with the x-axis. So we would say the missile that the rocket fires, the missile would intersect with the x-axis at 25/3, 0. And we said that's approximately 8.33, 0. And yeah, that looks roughly correct there for the location there. We said it was larger than 5 because this is an x value of 5. It's a little bit further to the right. 8.3 seems about right. And that is exactly what is done in the solution here. Okay, so hopefully, you know, when we are at this point here, the tangent line is this way. When the rocket is fired, hopefully the asteroid is at the location, you know, 25/3, 0. That way it'll get blown up. All right. And that is the end of this section on implicit differentiation. So hopefully we now know a couple of things: how to find the derivative of a complicated function using implicit differentiation, and you know, how to use implicit differentiation to find the equation of a tangent line. Okay, well that mostly relies on 3.81 to find the derivative using implicit differentiation. All right, hope you enjoyed the video, and we'll stop here.